Good morning, this is Dr. Beck with another chemistry video for GCSE Trilogy, Combined Science in the AQA specification. Hopefully you can see on the screen there the parts of the specification that we're going to be looking at today. You should also notice that some of this lesson will be for higher tier students only. Now, though at the moment we haven't decided which tier we're going to be in, I'm assuming that most of you, if not all of you, will be doing the higher tier. So today's video will start with foundation level work and then move on to the higher tier work regarding things called moles. Okay, if you want to have a look at that in a bit more detail or anything else we study today, please pause the video at any time you like. Okay, for this lesson, it's going to be really important that you are fully focused. So if you have your phone, please put it in a different room or turn it off, wait so it doesn't distract you. If you're using a web browser to look at YouTube, then please make sure your other tabs, any social media tabs, are turned off or closed so that they're not distracting you. And most importantly, when I ask you to have a go at a question, please, you should actually do them. That's the best way we're going to learn for this video and for future videos. Most importantly, make sure you have in front of you a pen, a pencil, and a calculator, which is not your phone calculator, an actual calculator, and a copy of the periodic table. You should have a copy of the periodic table in your planner, or you do have a copy of the periodic table in your planner, and you also have one in the back of your chemistry book. Either will do, they are basically both the same information. If you haven't got those things, pause the video and go and find them. Okay, we're going to start today with a little starter task, a do now task. It's not the same as a normal one, but a little bit of a challenge for you to refresh your memory and get you thinking about chemistry. So please can you turn to the back of your book and could you write down this symbol, 12(6)C. Now the question is, the challenge, the puzzle is, what does that mean? What does it tell you? Can you write down as much information as you think you know about 12(6)C using your planner if necessary? For instance, which element is it? What is its atomic number? What's its mass number? How many protons, neutrons, electrons does it have? How many shells of electrons does it have? What group is it in? Perhaps even what period is it in the periodic table? I suggest this should take you no more than about 3 minutes. In the back of your book, have a go at answering as much as you can, writing down as much information as you can. Pause the video and come back when you're ready. Okay, great. Hopefully you've written quite a lot there. This is what we've been studying for the last few weeks. The puzzle, the challenge, the question was, what does this symbol mean? What does it actually tell us? Well, this is the symbol for carbon. And it's in the periodic table, which means that carbon is an element. The atomic number of carbon is 6, the lower number, and the mass number, the atomic mass of carbon, is 12. That's the top number. The atom of carbon has 6 protons. That's what that little number, the lower number, the 6, tells us. An atom of carbon has 6 neutrons. Now this is a bit of maths. The top number take away the bottom number. Remember, the top number is the number of neutrons and protons. The bottom number is the protons only. And because it's an atom and all atoms are neutral, if it has 6 positive protons, it must also have 6 negative electrons. And how are those electrons arranged? Well, they're arranged in this electronic structure, 2, or 2.4. 2 in the first shell, 4 in the outer shell, in this case, the second shell. And therefore, we can tell that this must be a group 4 in group 4 of the periodic table. And maybe you also recognize, because it's got 2 shells with some electrons in, it is also in period 2 of the periodic table. So well done if you wrote down that information. Remember, all of this has come from that symbol, 12(6)C. This is our understanding of the periodic table and our understanding of atomic structure. Pause the video, purple pen, check your work, and come back when you're ready. Okay, can we now please turn to the front of our books And can we write, as always, our title for the first part of the lesson and today's date and the learning objective and keywords, please. And again, give yourself a few minutes to do that. Whenever you're ready, come back to the video. Right, for today's GCSE chemistry lesson, we're going to be looking at an important topic, an important idea in chemistry, this idea of relative masses of atoms and molecules. So we're going to learn what the relative atomic mass of an element is, so that we can then calculate relative atomic masses and relative, formula masses. We've just got those two key words. Now, you might be thinking, well, okay, what does it mean? What is it relative to? Why are we talking about relative masses? Why don't we just talk about atomic mass? All right, now this might seem a little bit pedantic, but this is the proper way to refer to these concepts today, where we're talking about the relative atomic mass and the relative formula mass. Let's start with a little model. On the screen, you can see a cartoon, which appears to show a bag of marbles. Now, the marbles are all the same. There's a few of them looks like got a bit of a light in effect on there, but let's assume all those marbles are the same and they are all small marbles. Now, because they're small, they're not going to weigh much. Okay, let's just not worry about the material they're made of. Let's just say they are marbles made of glass. That'll do. That's fine for our model. This is a second bag of marbles, but they're different. These marbles are all the same as each other, but they are different from the first type of marbles. Now, how are they different? Yeah, well, the most obvious thing is they are larger. These are large marbles. They are going to weigh more than the other marbles. Again, for our model, let's just assume they're all made of the same stuff. They're all made of glass. Hopefully you have the idea that they will weigh more than the other smaller marbles. Okay. These whole bags of marbles will have different weights. And we can also now use this word mass, which is the better word to use. So these bags of marbles will have different masses. However, have a look at the pictures. They're the same number of marbles in each bag. Okay, that's constant, that hasn't changed. What has changed is the sizes and the weights of each individual marble. Okay, so we can use this going forward with our idea of masses of atoms. Here's a symbol for hydrogen from your period table. Hydrogen is like our small marbles. It's the smallest, the lightest element. It has a relative atomic mass of 1. That's the top number. It has only got 1 proton, but no neutrons. It's the smallest element, the smallest atom, and it's a bit like our small marbles in our model. Let's have a look at another type of element, the first one from our starter. Let's look at carbon. This has a relative atomic mass of 12. Now, why? Well, as we've already discovered, it has 6 protons and 6 neutrons. This is the equivalent of our large marbles. Okay, each atom is heavier, has more mass than the hydrogen atoms. How does this help? 1 atom of carbon will weigh 12 times as much as 1 atom of hydrogen. Okay, just pause there just to let that sink in. The mass of an atom of hydrogen is 1. The mass of an atom of carbon is 12. So relatively speaking, hydrogen is much lighter than carbon, 12 times lighter, a 12th of the mass. So, using our word mass, 1 atom of carbon will have a mass that is 12 times that of a hydrogen atom. Okay. Now we can also scale this up. If we had 12 million atoms of carbon, they will have a mass which is 12 times that of 1 million atoms of hydrogen. Got the same number of these things. The only thing different there is the mass of the individual things. Okay, think back to our marbles. If you've got 10 small marbles and 10 large marbles, if we keep this ratio, then the 10 large marbles will be 12 times as heavy as the 10 small marbles. The ratio there between the masses of the marbles is the important thing. Scaling up, if we had 47 trillion atoms of carbon, they will have a mass which is 12 times that of 47 trillion atoms of hydrogen. Okay, the only thing that has changed or is different is the mass of the individual atoms. Okay. And here's where we come to this idea of relative mass. We say that one atom of carbon-12, what's shown on the screen here, has a mass of exactly 12 units, 12.000000 units. And this, therefore, is our reference point for all elements. Okay, we say that carbon has a relative atomic mass of 12. And then we can use this to compare to other atoms and other elements. One atom of hydrogen has a mass which is 1/12 the mass of carbon-12. Well, that's nice and convenient. Hydrogen has a relative atomic mass of 1. Great, so that's basically the top number you're seeing there. This is what's called the relative atomic mass now of hydrogen. It is 1/12 the mass of an atom of carbon-12. The relative atomic mass of carbon is 12. The relative atomic mass of hydrogen is 1. Okay, let's just breathe for a second. For the rest of the video, there's going to be two components. There's going to be one component next, which is going to be for the foundation level, and then we're going to play on and go through the higher parts of this particular part of the specification. Okay, let's take a breath. Okay, let's go back. Here we go. So we're going to look at these two symbols and what they mean. So remember, this is our relative masses of atoms and molecules, and we're learning about the relative atomic mass, so we can then calculate or deduce the relative atomic masses and relative formula masses. So the first bit is nice and simple, hopefully. Let's just have a look at this. First of all, the relative atomic mass. This is the abbreviation for relative atomic mass. If you wish to write that down, fine. Now, have a look at that carefully. The R means relative, and the A stands for the atom, the atomic mass. So the relative atomic mass of carbon-12 is, shout it out. Okay, yeah, 12. That's it. That's the top number. That's what it's telling us. Relatively speaking, the relative atomic mass of carbon-12 is 12. That's our standard reference point. The relative atomic mass of hydrogen is, shout it out. Yep, 1. Good. How about the relative atomic mass of zinc? Shout it out. Excellent. Good. So we're getting it. The top number. The top number is the relative atomic mass. So here it's 65. Well done if you got those right. Pretty simple. Pretty simple. But let's have a look at the next thing. We've done relative atomic masses. What about the next part, the relative formula mass? Let's have a look. On the screen, you should be able to see two spheres joined together to form a molecule. Now, I'm not going to tell you any more of that. You should know what that picture represents. A molecule of oxygen formed by two atoms. So at the bottom of the screen, you have our symbol for a molecule of oxygen. Because there are two, we have this subscript 2, this little 2, next to or after the symbol for oxygen. So O2. Now, what we're going to do is calculate the relative formula mass for this molecule. Okay, now this is the symbol for the relative formula mass. If you look in old textbooks or older websites, this may also be called the relative molecular mass, which kind of explains why we use a capital M. But for our specification for exams, it will say the relative formula mass. So because it's a molecule, oxygen, O2, we have to work out the relative formula mass of O2. So how do we do that? Each atom of oxygen has a relative atomic mass of 16. So we multiply those together, or we count the number of atoms that there are, and we multiply the relative atomic mass by the number of atoms that there are. And this is how we then show that the relative atomic mass of a molecule of oxygen is 2 times 16. So simply 32. Okay, a little bit more complicated now. On the screen, you should see the chemical formula for sulfuric acid, H2SO4. I'm going to give you a few minutes to calculate the relative formula mass for sulfuric acid. You will need a periodic table, however, in the top of the screen now, you should see some hints. So have a go at doing that. Pause the video when you've done. Think carefully about those different symbols and the numbers, and return when you've finished. Okay, hopefully didn't find that too difficult. Here's what's going on. The relative formula mass is the sum of the masses of the individual atoms. So we have two hydrogen atoms. Each one of them has an atomic mass or relative atomic mass of 1, so 2 times 1 plus 32. Now, there is no number after the S, so that means there's just one atom there. And then 4 times 16. 4 times 16. Because there are 4 atoms of oxygen present, we do the maths, we then come up with a number 98. Well done if you got that answer. That's basically as difficult as it gets for foundation. Okay, so well done if you've got that, you're making great progress. Okay, on the next screen, I'm going to show you some questions. I'd like you to use a calculator, show all your working in your books, use your periodic table to help you, and work your way through those questions one by one, doing as many as you can. If you're aiming for those grades 5, 6 and above, you should be able to do all of these. So here we go. Stop the video and return when you've finished. Okay, great. Can we please take out our purple pens? We're going to correct, we're going to annotate, we're going to review our answers now. So, relative atomic mass of sodium is 23. We can find that directly from our periodic table. Next one, what is the AR of an atom of neon? Well, AR means the relative atomic mass. So again, the same thing. This is 20. We can find that in the periodic table. Relative atomic mass of aluminium. Now, I didn't give you the symbol for this. Hopefully you found it. It is 27. What is the MR? So we've changed that now. We're now talking about the relative formula mass of a molecule of chlorine. Now, chlorine is quite peculiar. It forms isotopes, and there are 2 major isotopes which give it an average relative atomic mass of 35.5. Now, that often confuses some students. It is fine. That number is fine to use. We can use it for our calculations. We simply multiply 35.5 by 2. Well done if you got 71. Calcium oxide, 56. And sodium sulfate, a little bit more difficult, more calculations to do, 142. Okay, the relative formula mass, when we add all that up, 2 sodium atoms, 1 sulfur atom, 4 oxygen atoms. Add up the relative atomic masses and end up with 142. Great. Okay, we're now going to move on to look at the higher component of this part of the curriculum. So we have changed our focus a little bit. We've got a slightly new title. So if you want to make a note of our different title, however, our learning objective is very similar. And we're including now a new word in our keyword list. This idea of the mole. So if you wish to make a note of the new title, including that new keyword in your book, please pause the video and return when you're ready. Okay. It sounds odd, but in chemistry, the mole is, first of all, a source of great amusement for nerdy scientists like me. But it's an idea which is fundamental to chemistry. And to start off with, it's got nothing to do with the creature I'm showing you on the screen. It just happens to be the same word. Okay. However, this idea of moles is absolutely fundamental to chemistry. And actually, it's pretty simple, but it sounds more difficult than it is. All we're doing when we're talking about moles is counting atoms. That's it. It's a way of saying I've got some atoms. If I have 1 mole, I have this many. If I've got 2 moles, I've got this many. If I've got half a mole, I've got this many. Okay? It's all we're doing is counting atoms. Now, let's go back to our model we used earlier in the video, and let's just go over a recap. We've already discovered, using the relative atomic mass, that each atom of carbon is 12 times the mass of each atom of hydrogen. Okay, now let's look at this in a slightly different way. If we've got 12 grams of carbon, there will be the same number of atoms as there are in 1 gram of hydrogen. So this is a new way of looking at things. Okay, if I've got 12 grams of carbon, because each individual atom of carbon has a mass 12 times that of hydrogen, if we have the same number of atoms, there will be the same number of atoms as there are in 1 gram of hydrogen. Okay, now why have I chosen 12 in particular? Well, again, this is kind of our base reference point. 1 mole, remember a mole is counting atoms. 1 mole counts the number of atoms that there are in 12 grams of carbon 12. Okay, now it's just a number of stuff like a dozen or a couple or a gross. Okay, we use some words in English just to refer to a number. It's not actually a number, it refers to a number. If I've got a dozen eggs, I've got 12 eggs. If I've got a couple of eggs, I've got 2 eggs. If I've got a gross of eggs, I've got 144 eggs. Okay, here we're using the word mole. What number does the mole represent? It represents this huge number. Okay, now you need to know this number for the specification. And for our sakes, it is 6.02 times 10 to the power 23. Now, any mathematicians amongst you will recognize that that is a huge number, but we can summarize it like this. Now, as you'll see in a future video, this is called Avogadro's number. Now, we're not going to worry about that too much, but that will come up in future videos. So this number is just a way of counting. Okay, 1 gram of hydrogen contains 6.02 times 10 to the power 23 atoms. Okay, 1 gram contains 1 mole of hydrogen. 65 grams of zinc 65 is 1 mole, and therefore A mole is just counting. 1 mole of zinc 65 contains 6.02 times 10 to the power 23 atoms. We're just counting atoms. In summary then, the relative atomic mass of a substance represents the mass in grams of 1 mole of atoms of that substance. For example, if we look in our periodic table, we will see the relative atomic mass of sodium is 23. Have a look at the top statement, the first sentence. Okay, the relative atomic mass of sodium is 23. That means if we have 23 grams of sodium, that is equivalent to 1 mole of sodium atoms. And 1 mole is just counting atoms, 6.02 times 10 to the power 23. Now, to work out the number of moles of a substance, we simply divide the total mass of the substance by the mass of 1 mole of the substance. Okay, remember, 1 mole of sodium has a mass of 23 grams. So if I had 46 grams of sodium, how many moles would I have? Yeah, hopefully you recognize we would have twice as many, 2 moles of sodium atoms in 46 grams. For each atom, the mass of 1 mole is the same as its relative atomic mass, but it's in grams. So for instance, for sodium, 1 mole is 23 grams of sodium atoms. Okay, so that was AR and moles. Let's have a look at MR. It's very similar, but slightly different. So let's have a look at this. MR, the relative formula mass. We can also extend this idea of moles to molecules. So instead of talking about moles of atoms, we can refer to moles of molecules. And as before, we use the same number. 1 mole is 6.02 times 10 to the power 23 molecules in a sample of a molecular substance. Okay, so we can talk about moles of molecules, we can talk about moles of atoms. And here we have got O2, which is a molecule of oxygen. The relative formula mass, as we've seen before, is 32. So 32 grams of oxygen gas will contain a mole of molecules. This many, 6.02 times 10 to the power 23, beg your pardon, molecules of oxygen. 32 grams of oxygen, O2, would be the equivalent of 1 mole. If we counted all the molecules, there will be 6.02 times 10 to the power 6.02 times 10 to the power 23 molecules of oxygen present in 32 grams of oxygen gas. Okay, we're just counting things. Have a go at this. Let's have a look at this. Glucose. Glucose, really important, a product of photosynthesis and a substrate for respiration. C6H12O6. It has a molecular mass of this, 180. So this means if we had 1 mole of glucose, it would have a mass of 180 grams. Okay, let's go back. Its relative molecular or relative formula mass is 180. Therefore, 1 mole of glucose, 6.02 times 10 to the power 23 molecules, would have a mass of 180 grams of glucose. Notice we're just calculating the relative formula mass, and we're converting that into grams, and that's the mole. So, in a similar way, we can summarize. The relative formula mass of a substance represents the mass in grams of 1 mole of that substance. And as before, we have got an example. This time we're going to use water because that forms a molecule. That is a molecule. It has the formula H2O. Hopefully you recognize it then. That means each molecule of water has 2 hydrogen atoms and 1 oxygen atom. Its relative formula mass, therefore, will be 2 times 1 plus 1 times 16. So 2 plus 16 is 18. If we had 18 grams of water, it would contain 1 mole of water molecules. And again, we can do a similar thing as we did before. To work out the number of moles of a substance, we divide the mass of the substance by the mass of 1 mole. So once again, if we had 54 grams of water, how many moles would we have? Well, hopefully you recognize that 54 divided by 18 is 3. So in 54 grams of water, there would be 3 moles of water molecules. And again, for each substance, the mass of 1 mole is the same as its relative formula mass, but in grams. Okay, let's summarize. Let's write down an equation. There are 2 forms of this equation. One is for single atoms, like we'd see with perhaps noble gases or metals, or for formulas of compounds. So that's the 2 different forms. The number of moles is equal to the mass in grams divided by the relative atomic mass for single atoms. Or, if we have compounds, the number of moles is the mass in grams divided by the relative formula mass of that compound. Now note, the mass must always be in grams. So many times students fail to convert. They forget to convert kilograms into grams and the answer is wrong. Okay, so please ensure that the mass is always in grams. And also it says there the abbreviation for moles is simply MOL. Okay, now that's not something you need to worry about too much, but yeah, MOL is the abbreviation for moles. Right, as a final task then for this lesson, I'd like you to work through the questions I'm going to show you on the screen. Once again, you will need your periodic table. You're very likely to need a calculator. If you haven't got those, please go and find them now and come back when you're ready. This might take us 10 minutes depending on how quick you're working. Use your periodic table. Come back when you're ready. Okay, welcome back. Some of those are quite challenging. Let's have a look at the answers. I'm going to show them to you all at once. There's a degree of working shown as well, so let's have a look at those. So lithium, 7. Magnesium atom, the AR is 24. Both of those you can take directly from the periodic table. Fluorine, 38. MgCl2, 95. Complicated one here, aluminium sulfate gives us 342. The relative atomic mass of sodium is 23, so we would need 23 grams for 1 mole. For nitrogen, 14 grams of nitrogen gas, which is a molecule, would be half a mole, 0.5. And if we had 88 grams of carbon dioxide, this would equal to 2 moles. Okay, if you need to go back and review any of the lesson, just press rewind. Well done if you got all those right. We were going to continue for the rest of this week looking at similar concepts in chemistry, but here we've got our baseline. Today then we have looked at relative masses, relative atomic masses, relative formula masses, and for the higher students we've also continued to look at moles. For our next lessons I'm going to set you some tasks for Oak Academy lessons, and then next week we will have another review of what we've learned so far. Okay, well done for today, and please get in touch if you've got any problems or you'd like any further explanations. Okay, thank you very much indeed. See you next time.